Let's learn how to find the greatest common factor, or GCF. First, we'll learn how to find the GCF, and then we'll talk about how to factor out the GCF. Let's start by looking at how to find the GCF of two numbers. There's different ways to do this, but one way is called the prime factorization method. Let's use this method to find the GCF of the two numbers 12 and 8. The first step is to write each number into its prime factorization, which means write it as a product of prime numbers. Here's the prime factorization for 12, and here's the prime factorization for 8. This is the prime factorization because each of these numbers is prime, and if I took these numbers, multiplied them together, it would give me 12. If I took these three numbers, multiplied them together, they would give me 8. It's just a coincidence that in this case, both 12 and 8 have 3 prime factors. But the number could be different for different cases. Step 2, determine what factors are in common or shared between the prime factorization for 12 and the prime factorization for 8. First, we see that they have this 2 in common. They also have this 2 in common, but that's all they have in common. 3 does not belong to both factorizations, and the third 2 does not belong to both factorizations. So they both have a first 2 as a factor, a second 2 as a factor, but that's all they have in common. The GCF is the product of what they have in common. Take what's in common, multiply those together, and that gives us the GCF. So in this case, the GCF is 2 times 2, which equals 4. So the GCF of 12 and 8 is 4. We found it using the prime factorization method. One of the meanings of GCF is that's all the factors that are in common between the two numbers. So if you remove that common factor, i.e. divide by that GCF, the result, which we call the quotient of that division, will have no factors in common. So let's say we divide 12 by the GCF 4, divide 8 by the GCF of 4, which gives us 3 and 2 respectively, and 3 and 2 have no common factor. If they did, that would be an indication that we did not correctly find the GCF. Now, if you remember the prime factorization for 12 and 8, if you look at the factors that were left over from each one, the non-common factors, for 12 it was 3, for 8 it was 2, so it makes sense when we divide 12 by 2 times 2, which is 4, we should get 3. When we divide 8 by 2 times 2, which is 4, we should get 2. Just those leftover factors that were not in common when we found the GCF. Let's look at an example with variables and find the GCF of x cubed and x to the 5th. We can still use the prime factorization method. But this time, instead of working with a number, we're working with a variable expression, but the concept is the same. The first step is to factor each variable into its prime factorization. Using the definition of exponents, x cubed is just x times x times x. X multiplied by itself 3 times. X to the 5th is x multiplied by itself 5 times. So that's the prime factorization for each. Now step 2, determine what factors are in common between the two prime factorizations. They each share an x in common, they share a second x, and they share a third x. But that's all they have in common. X to the 5th has 2 additional factors of x that are not in common with the factors of x cubed. So we stop here. This is all the common factors. So what's the GCF? The GCF is the product of those common factors, or multiply those common factors together. We can rewrite this as simply x cubed. Thus the GCF of x cubed and x to the 5th is x cubed. Let's observe a really easy shortcut here. If you have like bases for example, here we have x cubed and x to the fifth. They have the same base x. So we have like bases. Then the GCF is simply that like base with the smallest exponent from the list. So here we have x cubed, x to the fifth. The smallest exponent is 3. Therefore, the GCF is x to the third power. So it makes it really easy to find the GCF of a list of variable terms. Now let's put this together. What if we have coefficients other than 1 with our variables? How would we find the GCF in that case? Here's an example. 12x cubed and 8x to the fifth. Let's find the GCF of these two terms. We've already looked at an example finding the GCF of a pair of numbers. We've already looked at an example finding the GCF of just the variables. So how do you find the GCF when you have them both together? Well, you find the GCF of the numbers, find the GCF of the variable part, and then multiply those two together to get the GCF for the entire term. Step 1, find the GCF of the numbers. We're to figure out the GCF of 12 and 8 was 4. Next, find the GCF of the variable factors. We're to figure out that the GCF was x cubed. So finally, to put it together, the GCF for the list of terms is 4x cubed. Take the GCF of the numbers, GCF of the variable factors, multiply them together. Let's look at another example. Notice for this example we have 3 terms in our list. That's fine, you could have any number of terms. The way you find the GCF is still the same. We can find the GCF of each like factor individually, then multiply the GCF of each of those like factors together to find the GCF for the entire list of terms. Similar to what we did in the last example where we had numbers and the variable part. In this case, all the coefficients are 1, so we don't need to worry about that for the GCF, but we have 2 different variables. So it's the same concept, to find the GCF of each like variable type and then multiply those GCFs together to get the GCF for the entire list of terms. So in this case we have a like base A and we have another like base B. First let's find the GCF of the A like base variable factors. Remember the trick we talked about when you have like bases? The GCF is that like base raised to the smallest exponent. The smallest exponent is, in this case, 2, so the GCF equals a squared. Now let's look at the factors with a like base of b. Again, the GCF is the like base with the smallest exponent. In this case, for the b's, the smallest exponent is 2, so the GCF equals b squared. Now we need to find the GCF for the entire list of terms. We do this by taking the GCF from each of the like base factors, which was a squared for the a like base factors and b squared for the b like base factors, and multiply those two together to get the GCF for the entire list of terms. So the entire list of terms GCF is a squared times b squared. Except we typically don't write the multiplication symbol because we know it's implicit. In that last example, we used this helpful hint where the GCF of like bases is just the smallest exponent on that like base. Let's do another example. In this case, we have 2 terms we're trying to find the GCF of. We see we have these exponents. What's the base of the exponent? Because there's parentheses, that extends the reach of the exponent to everything in the parentheses. So the base for this first term is x plus 2. The base for the second term is x plus 2 as well. Remember, the GCF of terms with like base is the base with the smallest exponent. So what's the GCF of these 2 terms? Well, it's the base, the like base, which is x plus 2. But what's the exponent? The exponent is the smallest exponent from the list on that like base, which in this case is 2. Therefore, the exponent for the GCF is 2. So the GCF is that like base, x plus 2, raised to the second power, since that's the smallest exponent. The base for this example was a little bit more complicated than the base we saw in a previous example, but that does not change the concept. It does not change how you find the GCF. So do not let that intimidate you or distract you from how to find the GCF. It does not change anything, the fact that we have x plus 2 as our base instead of just an x. We learned how to find the GCF of a list of terms.